I'm going to begin this talk by just defining an action with no context on homogeneous polynomials of degree 2. We're going to act on this guy, and the action is going to be defined as follows. We're going to send x to, let's say little a, x plus b, little b, y, and we're going to send y to c, cx plus d, y. Now let's substitute these transformations into this polynomial. We get the following. Let's group the like terms of this thing. I'd like you to notice that each term here is a linear combination of a, b, and c. So we can write this as a linear transformation of this guy according to the following matrix. This is also a linear transformation, but on the variables x and y. In fact, we can write it like so. At this point, I'm going to state where this matrix is coming from. As I mentioned at the start, I'm talking about a group action on homogeneous polynomials in two variables of degree 2. I'm going to say it's coming from this special linear group of degree 2 over the integers, which means that this is a 2 by 2 invertible matrix with coefficients from the integers and determinant 1. To recap this action, if we start with a set of homogeneous polynomials in x and in y in two variables, and we define an action on x and y according to this transformation, we induce an action on the coefficients of the polynomial, which live in, affine 3 space over the integers. And then supposing that x is closed under this action, we'll end up back at x, but at a new f, so I guess where the element over here is the coefficient of the polynomial m of m acting on f. The question that I immediately have is, what does closure look like? If I start with just one polynomial, what does the smallest set x look like that is closed under this action from the special linear group of degree 2? To explore this question, it's important to understand the invariance of a polynomial under this action. I'll start by writing down an important one that you're all familiar with. The important invariant that I'm going to be talking about is the discriminant of this polynomial. You may recall that the discriminant here is going to be b squared minus 4 times ac. I claim that the following is true. Let M be a matrix of the special linear group of integers. I claim that I claim that this is true. So let's start with x squared plus xy plus y squared. And let's consider the action of using the transformation over here. We'll end up with a corresponding transformation on the coefficients. And now let's calculate the discriminant of this thing. 1 plus. And then if we take and then we compare this to the discriminant of f, and we're going to get 1 squared minus 4 times 1 times 1 equals minus 3. Lo and behold, here's why. Let's let m equal, it so happens that, and because this is equal to the determinant of m, and because m is in the special linear group, it has determinant 1. So this is the discriminant of an original function, like I said. So we know off the bat that every element in the, I guess, you know what? Let's call f every element in the closure of this set under the action of the special linear group is going to have, let's just let G in here, and we have the property that, then the question becomes, is every such polynomial with the same discriminant as f and integral coefficients contained in this set? Exactly how many of these are accessible through these linear transformations? In service to this question, I'm going to talk about some work that Gauss did when he was a teenager. Gauss was playing with quadratic forms, which are exactly what we've been looking at so far. Things of this form. You know what, I'll include a 2 in there, because that's how Gauss did it. He was taking x and y to be from the integers with this condition that's equal to some other integer. He writes this thing as a form, the triple A, B, C, and he says that m is represented by this form if there exist integers x and y such that the equation holds. First, Gauss demonstrated that there exists an integer such that there exists an integer chi congruent to the discriminant divided by 4 modulo m, where chi is related to a specific pair x, y together with a transformation from SL2. He goes on to define equivalence classes on quadratic forms by stating that two forms are equivalent if they differ up to a transformation of x and y by SL2 in the way that we did earlier. And there are two major questions that he's after. The first question, I'll use Gauss's language. He says the quadratic form f, and if the discriminant of f equals discriminant of little f, are f equivalent? That's the first big question. The second big question is, given the form f, can an integer m be represented by it? This is equivalent to asking if there's an integral solution to this equation. This is essentially the question that I'm interested in. If we take the collection of all polynomials that are we know off the bat that this is going to be contained in the set of all. So we start in this set, and then using Gauss's solution to this question, we're able to chop out everything that we don't want in there. And that will demonstrate the closure condition. I'm going to skip right to the result. No, I will not jump right to the result. This result is the culmination of 200 pages of Disquisitiones Arithmeticae, and I cannot cover it. So, here is one of the first results. The first ingredient in answering this first question is if we have one such transformation, M in the special linear group, from big F to little f, we're able to access all of the other forms we're able to access all other transformations that take f from little f, that take big F to little f, according to something that looks like a Pell's equation. A, B, C, prime, B prime, C prime. It turns out that it's kind of hard to write on the whiteboard and talk at the same time without reading off very slowly what I am writing. Here I have the condition that the determinant of m equals the determinant of m prime because Gauss was considering linear transformations with determinant plus or minus 1. If these conditions are satisfied, then if you are able to find these two integers, t and u, such that t squared minus d u squared equals m squared, where d is equal to the discriminant of f, and m is equal to the greatest common divisor of a, b, and c, you're able to find every such m prime by finding integers t and u that satisfy this Pell's looking equation. Now, if we were to divide this by m squared and take the rational numbers t by m squared minus d u by m squared, and work with the Pell's equation that we're familiar with. Here, I forgot that a Pell's equation is specifically a Diophantine equation. This is not a Pell's equation, but it has a similar structure, so I think that it would be interesting to share. We actually wouldn't be able to access all of the solutions because we don't want all rational numbers, t by m and u by m. We only want rational numbers whose denominators are m. We can view this as a Pell's equation on the complement of the localization of the integers at the ideal generated by m. When I set out to do this project, I was hoping to learn a bit about algebraic groups, that is, groups which are also varieties. There's some issues here. When I tried to crack into this stuff, there's a lot of language of morphisms and sheaves, and we didn't get there. So here's the idea. You have a group G that is also a variety X, and in the composition law, G, let's just call it plus, is a morphism in X, and also an inverse is let's call it in, is also a morphism on elements in X. And an example of this, and I'm just going to give an example of this because I would like to. An example is the general linear group of, I guess, degree n over a field. And the reason why this works is you can take, and the reason why this works is if you take an element, a matrix in here, because M is invertible, we have the property that the determinant of M inverse M equals 1 equals the determinant of the identity 1. And this is multiplicative, so we have the determinant of M inverse equals 1 over the determinant of M. And these are polynomials. So if we just take all the determinants and take these, take multiplication of determinants to be the group composition law, allegedly this is a morphism, sue me. In class we looked at elliptic curves as algebraic groups. These elliptic curves were algebraic groups. We saw this by, the group structure was defined according to the chord tangent method. To conclude this presentation, I will share with you some things that I've heard about, but I don't know very much about. The capstone, I guess, as it's been presenting to me, of Gauss's work is his theorem of quadratic reciprocity. For primes, for odd primes, Q and P, not both 3 either. There exists in x squared, an integer x squared, congruent to Q modulo P, if and only if the same applies to P mod Q. And proving this is very involved, and this appears to be at the end of Gauss's writing on this stuff, and also at the, this is how another author, this guy, Flath, I like his book. Flath wrote a book on number theory. It's basically what Gauss did. Gauss's own work is called Disquisitioni, I think Arithmetica. Flath is writing about this stuff. This stuff is written by Gauss. And Gauss wrote this stuff when he was a teenager, and I think that's awesome. Seems like he had such a fun time. There's about 300 pages of textbook and examples that are stopping me from fully appreciating and understanding this work, but I think that understanding Gauss's study of quadratic forms will add to my library of examples, including the Huron triangles and the Pythagorean triples. In this class, we've been exposed to varieties in the context of questions like, how many rational points are there on this curve? Where are they? I want integral solutions. And I believe that Gauss's study of quadratic forms will be another great example to add to this collection. This kind of stuff has a flavor of the fundamental theorem of calculus and of Frobenius reciprocity. This topic of reciprocity is very exciting to me, and I would like to see how it emerges in varieties. So that's the next steps for this project. So let me just recap the things that I talked about here. I talked about the action of I'm just going to call it the next step here is the following question. As we've seen in this course, you can take your prime ideals and view them as points and view them as points in your coordinate ring. As we've talked about in this course, something similar is happening here. We can take a polynomial, or we can take its coefficients. I don't understand how this mapping talks to prime ideals and maximal ideals, so that's another step in this project. And I've written Nullstellensatz where, because that's the question pretty much. The next question is closure. Closure of set of polynomials under the action. I showed that the discriminant is invariant under this action, and but I don't know what exactly ends up in that set. The third topic I talked about is quadratic forms. Equivalence classes have same discriminant. So these two questions can be used to study each other. Fourth, I talked about algebraic groups. Well, I talked about I would like to know these things. And finally, I briefly mentioned quadratic reciprocity. If this seems like too much for this presentation, that's because it is, and I had trouble going into depth here. I believe that I'm a little bit frustrated by my lack of vocabulary. I hope at the very least that I've been able to show you a cool or unfamiliar idea. In recent months, I found that randomly sampling elements of sets and looking at the properties of those samples can actually be a very enlightening way to understand a collection of objects. So another idea to explore this set of polynomials closed under transformation of special linear group is to do a random walk on some free generators for the special linear group. The following matrices are generators. These two, by taking all powers of these in whatever orders and closing that collection under inverses, you end up getting all of the special linear group. If you do a random walk on these elements, I think that the sets that you generate with this will be very helpful for understanding the general properties. These are simple transformations for starters. So if you want to play with these things for fun, write a computer program or calculate some things by hand, I think that these would make some simple fun. Over the last two breaks, I've just been playing with numbers randomly, whatever questions I have. But it appears that Gauss is more talented than me, so I might follow what he's done and learn a thing or two.